I used to be a VP of engineering for an energy company where we had lots of fun. And then I went to TypeSafe and became a senior software engineer, and now I'm a principal systems engineer at Lightbend. We changed our name, so you get a new title too. That's kind of nice. And been building distributed systems for a long time. We have a book out that Manning is the publisher. It's called Reactive Application Design. There's three of us authors, Sean Walsh and Brian Hanafy from Wells Fargo. So if you're looking for, I actually have some discount codes. If you're interested, let me know and I can give them to you. And my Twitter account. Of course, you know about us and Lightbend. Probably one of the things that we're most famous for is the Reactive Manifesto. And it's kind of a philosophical way to design these distributed systems. And so at the top of this puzzle is this idea of being responsive, ready to respond to stimulus. And there's, I think, over 20,000 signers now, or 21,000. And, it was started by some pretty smart guys, Jonas and Roland and Dave and so forth, and Martin Thompson. So if you haven't read it, go out and check it out. So I like this picture of how to describe a reactive system. The idea is at the top, it's responsive. That's the most important thing. People don't care in life, they don't care in software, they don't care in relationships. If you're not responsive, then they sense a problem. Either you're being disrespectful or you don't care or whatever. So generally people accept if you respond, even if you don't necessarily give them the answer they want at that time, both in software or in relationships with people. So how do we become responsive? Well, life has issues, right? Things happen. You get sick, or your software system, the load becomes too high, or whatever. So you have to be able to deal with that. So to the left and the right, we have these two things, resilience and elasticity. For us, resilience is not fault tolerance, it's self-healing. So built in the DNA of your application, it needs to recognize it's having a problem and then take the steps to correct it without human intervention. And then elastic means it needs to sense that the requirements or the load that's put upon it is increasing or decreasing, and it needs to scale appropriately. So if it's decreasing, you want to scale down so you don't spend as much money or use as much CPU time. And if it's increasing, obviously, you want to scale up. And at the bottom is this message-driven architecture, which we could call, response-driven, event-driven, whatever. The idea is you have a basic message that's being passed back and forth. So you can see that the arrows from elasticity and resilience point up to responsiveness, and they also point to each other. So they kind of have this symbiotic relationship. Sometimes, in order to be resilient, you have to employ elasticity, right? So the load's becoming significantly greater, and you don't want your application to crash, so you're going to spin up more servers. And at the bottom is this message-driven concept where everybody's going to communicate back and forth with messages and rely on this evil thing called eventual consistency, which we'll talk about. So one of the things I'm sure you guys are familiar with is some of our products is ACA and Play and Lagom and so forth like that. ACA is kind of like the substrate for all of our products. It is underneath of Play. It is underneath of Lagom. It's an actor model, and it provides all the features of reactive style design that we're looking for in these types of applications. We also have all of our open source offerings, and then we have some commercial offerings with our subscription, things like Split Brain Resolver and Cinnamon, which is our telemetry gathering software and so forth. So the last thing is we have this new thing which is becoming more and more important called our fast data platform, and it's the recognition that data is a very important thing, but it's also time sensitive. So if you're going to be competitive, you need to begin to understand how to digest your data in ways of real time or near real time and be able to make decisions based on that. And we're going to talk about something called feedback control, which is pretty popular in mechanical and electrical engineering, but in computer science, software engineering, it's kind of new, right? We're starting to explore how to do it because of the way software works as opposed to a physical piece of hardware. So for the talk, we're going to talk basically about these ideas. Excuse me. We'll talk about microservices so we can get into an agreement of what they are, because they mean different things to different people. We'll talk about something called promise theory, which doesn't come from computer science, but I think applies to it very, very well and is foundational in how you think about designing an application. Event sourcing, CRUD, create, read, update, and delete, fast data, and then we'll talk about feedback control, which I think ends up being the culmination of all this type of stuff. So first, microservices. So what are they? One of the definitions that most people use, which I think is a great definition, is this idea of you have these autonomous systems that are created by a group of people. They can work independent of other groups. They can develop, they can deploy, and they can push it out into production and so forth. And they can manage them independently. So that's kind of like the operations side of a microservice and maybe your development philosophy. But in reality, a microservice, I think, is much more than that. The way that we like to look at them is they're a system of autonomous, collaborative, distributed services. And that's a mouthful, but autonomous, autonomous from the Greek, which means self-governing. So your microservice, regardless of what happens in the rest of the world, it still stands. It still works. So if your microservice needs weather data and you're pulling it from NOAA or somewhere, and that interface goes down, if your microservice doesn't have weather data cached for the significant, whatever your SLA says, then it's not successful, right? It's not going to be able to deliver the information it needs. So as a microservice, or think of it yourself, are you going to rely on other people to make you successful? No, of course not. You're going to learn what you need to learn. You're going to do what you need to do in order to get there. And it's the same thing with your microservice. Collaborative, obviously, it's a community, right? A village, right? Everyone works together to achieve a greater goal. So those two pieces of a microservice are very, very important. And so the question ends up becoming, how do you become autonomous, truly autonomous, self-governing, being able to stand on your own? So as we look at some of the key concepts is, the first thing I would say is you're going to take a look at something called promise theory, and it's a way to think about how you operate with other people. And then obviously you're going to, there's some argument here about whether micro means small or not. I like to keep them as small as possible because then they're easier to reason about and they're easier to test. But I think the boundary of a microservice is determined by the business, not by the developer. And that's something that you have to think through and talk through the business folks and things like that. It's like eventual consistency. I'll get asked, well, how long is it going to take? And my answer is always, I don't know. You tell me. How long do you want it to take? How long do you need it in this particular use case to take? Don't tell me 10 microseconds because you just like it to be fast. Literally, seriously, how important it is. If it's 500 milliseconds or 100 milliseconds, then we'll do everything we can to make it that fast. Otherwise, it might be a minute or 5 seconds or whatever, and so forth. So as you push the boundaries of things like eventual consistency and require a stronger consistency model or real-time updates, it's going to cost more, right? So those are the things that you have to balance out, cost versus value. Cluster your services. So each microservice, I feel should be clustered, unless if it's maybe your kid's soccer site or something that may not make sense. But for business applications, for the most part, clustering is a great way to infuse elasticity and resilience into your application. And as I had mentioned, your consistency is based on your SLA at the end of the day. So your consistency model, the speed at which your data is processed, all of that really is tied to a business decision as to how important is this particular transformation of data or whatever to the business. That's going to define those boundaries. And the last thing we like to say with this is, because the system is going to be autonomous, and self-governing, it needs to have its own data, right? It can't rely on a federated Cassandra database to pull its data from. Each microservice should have its own unique, distinct data store, whatever that means. It could be a cache, it could be a full clustered instance of Cassandra, or it could be MySQL, whatever. It should have access to its own data, so when the rest of the world collapses, it can still stand for whatever time the SLA says it needs to. So polyglot persistence is a good way to take a look at that. So some of the things, as we move into this world of microservices, we need to recognize is what we're really talking about is distributed computing. And that's a totally different beast than what we're usually used to in a monolithic style application. So in distributed computing, you have these boundaries inside your microservice. That's a safe area, and between is just the wonderland, the internet, the network, and all kinds of craziness can happen in that area. So you need to accept that and understand it. And in doing so, in regards to data, it presents some interesting things to you. When you take a look at data across your entire application, which could be 10, 20 microservices or more, the data that is stored locally that you process in your storage is your inside data, and it is your current reality. It is present. It is now, right? That's the only real true data that you can say, I know what that value is, and that value is valid. Any data you receive from the outside is always historical, even if you just received it a millisecond ago. It is always past data. There is no guarantee that if I pull data from microservice B, that when I pull that the value is still that in microservice B. There's no way to guarantee that, okay, in distributed computing. So you need to recognize that and understand what that means to the business. And then asking, right, or requesting is a hope for the future, right? We always have that discussion in ACA about guaranteed message delivery and do you need it and all these kinds of things. So in these types of systems, the things that we need to recognize are these three states of data and how does that affect my particular service that I'm designing. And ultimately, we say own your own data, as I had mentioned before. I think the real shocking thing that really takes a while to accept is it doesn't matter what storage medium you have, whether it's hot, warm, or cold, you're always looking at data from the past except when it's local to you. So as a design, this is the style that we would recommend. You see on the left side, it is basically separate services, and so you could build this really nice microservice distributed system and then use a single database that's clustered, and you kind of broke all the rules. So we would tell you to do it the other way on the right-hand side. And the thing that's funny about this is a lot of people will say, well, I got to synchronize my data, and what I like to say is just stop for a second and think about your life. Your entire life is based on messaging. It's based on eventual consistency. You'd think financial institutions, right? They're kind of important. They monitor money. If they had guaranteed message delivery, then we wouldn't have overdrafts, right? In inventory, we wouldn't have back order because you just simply wouldn't be able to do it. But the reality of it is we have both of those in those industries, and the financial industry is a very mature industry in many ways. So as we embark on this adventure in distributed computing through microservices, there's, I think, a different way of thinking that we can either learn, I wouldn't say the easy way, but we can also learn it the hard way by feeling all the pain of trying to apply our old principles. So one of the things that I think is really neat and very helpful is this idea of promise theory by Mark Burgess. If you haven't heard of him or you haven't heard of it, I highly recommend you get his book and you read it. And I think he has a powerful metaphor of how to reason about these types of things. So a promise is a declaration of intent whose purpose is to increase the recipient's certainty about a claim of past, present, or future behavior. Right? So if I promise somebody something, the purpose of that is to increase that person's reliability on me, or the fact that they're going to say, okay, he said he was going to do that and he did do it. And the reason that this becomes important is that when we build systems, especially distributed systems, a lot of times we make a mistake of making two systems coupled together. And what ends up happening is, in order for my system to be successful, I'm going to oblige the other system, right? I'm going to place an obligation on that other system to give me their data. And so what I've just done is I've tied my success, my ability to perform, to someone else's behavior, of which I have no control over. I can't make that system do anything. So if you just stop and think about that, and how you apply that to system design, it becomes a very important concept. So we would say, think in the idea of promises, not obligations. So when we talked about these autonomous systems, it leads to this idea of where your information, in order for you to be successful, is local. So when you're making a promise, you kind of start out in a vague kind of area, and you move towards a more stable environment. Whereas with an obligation, it's the exact opposite. It's very defined. You know what you have obligated somebody to do, but there's no guarantee it's going to occur. So you diverge. And with a promise, you converge. It comes from physics, but the idea here is that you need to set yourself up in an environment where you will be successful. And so you have to figure out what that is. So what we say is a microservice can only promise its own behavior. Okay? If, for example, I say, I promise, Jeff, I will pick you up at 6 o'clock. Okay? And in order for me to do that, I have to rely on Uber or a taxi or maybe Zipcar or something like this. As I start to go through that process, okay, no taxis, 30 taxis go by. You know, I do my Uber app. This has happened last night. 30 taxis go by. I start up the Uber app. It just doesn't work, right? So I had to reboot the phone and do all this other stuff. If I did not give myself enough time to manage those circumstances, then my promise would fail, and I would not be able to be there on time. So that's what I can't rely on Yellow Cab or Uber or any of these things. I got to figure out what I need to do to make sure I'm there at 6. So that's my promise. The more my promise comes true, the more reliable I am as a service. And you can think of it this way. I'll go back to weather data. You could have multiple sources of weather data, and some will be more reliable than the others. And as you begin to track that information and review that telemetry, you can hit the service that's most reliable more often, and then only roll over to the other services when the primary service fails. And you can track all that stuff and make decisions computationally as how to do that. So that's the basic idea. So promise your own behavior. As I had mentioned, obligations diverge and become problematic. All right, so anybody in here not familiar with event sourcing? Good. Oh, okay, good. So we can kind of go through this. I want to make sure we get into the later stuff. So as we all know, event sourcing is the idea of capturing events. And one of the great things about event sourcing is that it's an additive structure, so it's very easy to shard. Okay, and it's very fast. So you're doing append only. So you create a hash for the key, you insert it into the database, whatever storage that you're using, however you're persisting it, and it becomes very, very powerful. It also gives you the ability to take a look at the behavior of your system and play with it. You can go back in time and you can kind of sandbox some of the data and change some of the values and see what would have happened. And you can kind of run through these what-if scenarios. You can also begin to observe behavior about things that perhaps you may not even have thought of, and so forth. So event sourcing becomes a really powerful way to reason about data. More mature systems, if you've ever watched Greg Young's video, he points out more mature systems use event sourcing by nature. It's like your bank. Can you imagine if your bank used a CRUD, current state model? They never stored transactions, they just updated your current balance. Then you go to reconcile your account and you're off by 10 grand. They say you have 10 grand less, and you call them up and they say, oh, well, sorry, we're going to have to implement event sourcing in the next sprint so we can begin to track that for you. I mean, that's ridiculous. But we build systems like that, and we actually use those same excuses when we get a request that we never even dreamed of. CRUD, we know what CRUD is. We're very familiar with it, and I'm a big event sourcing guy, but I will also say that there is, I think, time when CRUD makes a lot of sense too. There are systems where historical data really doesn't matter. All they care about is the current state of something. So as data gets fed in, then they don't care what it said 5 minutes ago or 10 minutes ago. So why go through the hassle of storing all that data and so forth? And I think those are reasonable arguments. But as we know with CRUD, we have this relational model. And a relational model is very, very powerful, and especially for querying. And also the idea of there's no duplicated data in an event source-based system, especially if you're using CQRS. You're going to have tons and tons of duplicate data. And that's okay, right? That's okay. But you have to recognize that and deal with it. In CRUD, you have generally some type of backing model with an object relational manager, and it's going to basically do event sourcing under the covers temporarily and cache it and figure out the differences between your updates and your deletes and so forth, and then flush it into the database, which is going to do the same thing, and then finally commit it. And keep a transaction so it can roll back if you've wrapped it in a transaction. So, so you end up getting this type of model where you have an order line table and an order table, etc. And so we have these two different models. Event sourcing, one of the challenges with event sourcing is the number of events you have, so you snapshot your data. So all these problems have been worked through and figured out. But they're both components of microservices. You have to make the decision, again, from a business perspective, which persistence model makes more sense for me in this situation. All right, so fast data, what is it? Fast data is an up-and-coming concept. Actually, it's funny, a lot of these concepts are much older than we might think they are. In the energy industry, we have something called a SCADA system. And the SCADA system is basically event sourced based and processes real-time data, and it's been doing it for 40 years or more. So that these ideas aren't new, it's just they're coming into more of the business realm. And fast data is the idea that we're going to process data as it arrives, and that will lead to a better understanding of what's going on. What's interesting, though, in fast data is that because you're only getting a little piece of the picture over some temporal boundary, you have to be careful that you don't make an assumption which is not true, right? Have you ever watched the news and the news has a tendency to kind of conflate what's going on, and so you're thinking, oh, I'll come to New York City, it's one of the most dangerous cities in the world, I'm going to get mugged and all this other stuff. If you don't live here, you're not used to it or whatever. And that's because you get just a little piece of real-time data. You don't have the full picture of it's interesting, in Midtown, right, Chelsea, that area, that's actually the highest crime rate in the city. And it's basically pickpocketing and stuff like that. So keep your wallets in your front pocket when you're walking around. But there's no real violent crime or anything like that. So fast data is this thing that's coming in. And one of the interesting things is we get it from a whole a host of different locations, right? We can get it from IoT, we can get it from mobile apps, we can get it from other servers via headless, and all kinds of stuff. We can pull it from legacy systems, we can pull it from data lakes, all this kinds of things. So it's this idea of data coming in from everywhere. The thing that we have to recognize about fast data is the temporal boundaries that we create. There is no beginning and end. That's one of the first challenges. Whereas in a regular system, there's generally a start, an origin, and a destination. In fast data, they're synthetic, right? Those boundaries are synthetic. So I use our energy example. We had synthetic boundaries that were 14 days, with now being the center point, and that scale always slid. So if it was older than 14 days, it would drop off. We would do things like time series data and bitemporal time series data, where you would have multiple values for the same time slot, and they would come in. So the 7 days ahead would be predicted, the 7 days behind would be real data, and as that thing slid, they would update. And then you would make decisions based on the updated data that came in, and you would continually, and this is what we're ultimately getting to here, is you would have a feedback control loop. to make decisions on. So fast data, we have these, really the biggest thing I think is we have these notions of this temporal boundary. And the other thing that fast data does too is we can get a horizontal slice or a horizontal view across our microservices where we really weren't able to get that before. So how do we do that, right? One of the difficult ways is figuring out how to do that if every microservice has their own persistence, right, has their own data. And one of the ways to do that is through something like a queue or whatever you're using, a data backplane as we call it, right? And that data backplane is kind of like a river, right? And all the microservices are little villages sitting around the river, and they all have their own purpose and everything. Generally, people don't go down to the river every day to get something to drink, right? They dig a well, and a local well, or they go down to the river and they fill up on water for days and weeks and so forth, or they cut estuary from the river back to the village. So they're creating their own local persistence by doing that, as opposed to having to go down to the river every day. So that I think is one of the really cool things about fast data. But the danger becomes is how do I recognize those temporal boundaries? So when you're doing like machine learning or you're doing statistical regression or something like this, you have to take that data in and then kind of take in historical data and train whatever your model is and go through this process of looking at, is this data acceptable? And ultimately what you come down to is determining, and again, this is determined by the business, what is the acceptable delta of error for this particular process? Okay, so if it's between 3% and 8%, as long as I'm in there, I'm good. There's always going to be errors, right? It's never going to be perfect. So how do we do that? Well, we have this thing. You guys, anybody here not have a thermostat in their house? That's good. So thermostats are kind of like the canonical example of feedback control. Depending on the type of thermostat, every minute, every couple minutes, every couple seconds, they're going to take a temperature reading. They're going to compare that to the current temperature that they are sensing. And if it's high, then they're going to turn up the air conditioning. If it's too low, then they're going to turn off the air conditioning. They may even, if you have it auto-sensing, it may even turn the heat on for a little bit. And it's going to keep doing this nonstop, continuously, until it gets the right temperature. And then, of course, based on your insulation of your house and all this other stuff, it's going to just do this forever. And that's the idea that we're coming to in microservice design is how can we implement this? It's going to take more than just using something like ACA and building a some type of federated system. It's going to take more intelligence. We got to think about how are we going to handle this. And there's different ways. You can use machine learning and different types of optimizations. And depending on your return on investment, you can determine whether that's successful or not. The other thing you can use is statistical regression. And that's why I was talking about a delta of error. So if you run your model through MATLAB or something like that, and then you run it through just a Excel and a statistical regression, the MATLAB model is probably going to be more accurate. However, what you have to determine is the cost of implementing that process worth the difference in the preciseness of the model. So the idea here is feedback works by constantly comparing the actual behavior of a system to its desired behavior. If the actual behavior differs from the desired behavior, a corrective action is applied to counteract the deviation and drive the system back to its target. Right? Straight out of the dictionary, or our favorite one, Wikipedia. So things about feedback control is it's very isolated. It's very functional for those of you who love functional programming, right? It's very set to a particular idea. I'm going to observe this particular behavior. That's all I care about. I don't care about anything else, and I'm going to take whatever corrective action I need to drive the result of that behavior back to the target or the desired target. So you're kind of nudging it, self-correcting it. And as I had mentioned, is you got to be careful here that not the final bullet, But the second to last bullet, you got to be careful not to overcorrect. So what you have to understand is, I took a scuba diving course in college, and the instructor said to us, he said, "You think you're here to learn scuba diving?" And we're like, "Yeah, that's why we took the course." He says, "No, you're here to learn basically what I'm going to call controlled panic, right?" He says, "I'm going to teach you how to control yourself in a panic situation." And one of the things he did is he would not let us pass the class until we jumped into the deep end of the pool with a 20-pound weight belt on. And he wanted you to feel like it was drowning. And you had to release the weight belt. And you would go through this exercise because people would start to sink, and he'd jump in and pull them out until they could learn to release their weight belt. And the reason is one of his students 2 years ago, or this was many, many years ago, but 2 years prior, had gone scuba diving, and she panicked, and her regulator fell out, and she couldn't find it, and she didn't release her weight belt, and her partner just shot to the top. So she ended up dying. And so he's like, that's not happening ever again. So you people need to understand how to do it. And so the idea with feedback is control that panic. You're observing a situation. You have a very small amount of information. You're very focused, and understand that you want to make sure that you don't overcorrect. This is common in monitoring, right? We call it alert fatigue. If I have a threshold set and that threshold gets violated, and then I send out an alert, it's like a car alarm, right? How many people rush to see if someone's breaking into your car when your alarm goes off? Right? Nobody does. It's the same thing in monitoring and this type of stuff. So you have to be careful not to overcorrect, and that requires you to have in-depth knowledge of the use case that you're implementing this in. So ending up here, we have the difference. One of the problems in computer science is the behavior is less constrained, right? It's not the same as building a bridge or whatever, right? And the physical sciences and mechanical engineering and civil engineering, yeah, they're really amazing, but there's set factors. You know the basic weather conditions, you know the current of the river or whatever. In software, I mean, how many times has a sales rep, right, or a manager came to you, and they have sold a new feature that doesn't exist, and they're like, "Oh, you're smart. You can just implement that. What do you think? You need a couple days? Is that good?" Right? Anybody not experienced that? Okay. So, you know, the idea is in software, it's much more of a moving target. So, the other thing in feedback control is thresholds versus anomalies. Thresholds can be very misleading. One of the things is like actor mailbox size. If it is over a certain number of messages. In that case, that may be bad for this system, but it may not be bad for this system. So if I flag that, if that's kind of like my default, and I flag it, it's good for system A, but for system B, it's alert fatigue. So it's better to do anomaly detection where you're going to capture several readings. You're going to know basically what the reading should be, and then you'll smooth the data. So if your readings are 30, 30, 30, and then you get 200, and then 30, 30, 30, are you going to alert on that 200? Maybe, right? You have to understand your system. If you get, and then you get another 200 and another 200, then you might say, okay, there is a problem. It could be that one is just an outlier, right? So these types of things become very important in these types of systems. So ultimately, this is what we end up having. We have a disturbance that comes in. We have input into the system. We have a status. We measure it. We check that value against whatever our set point is. If there's an error, then we go down to the controller. We go back through the effector and then go back up to the where the disturbance had. And we just continue to do that loop until we have the set point that we want. So just to recap, these concepts and the purpose of my presentation is that when you're building microservice systems, microservice-based design systems, you know, it's a catchword, microservices, the cloud, you know, it's what are they? You're building distributed systems. When you're building distributed systems, there's some very important concepts that you need to understand. And I would say that promise theory, obviously event sourcing, and feedback control are maybe feedback control the most, or in Promise Theory, are new concepts to most of us. And it's very much worth taking the time to investigate them and apply them to your system design. So that brings us to the last section of our discussion, and that's building systems. Now that we have an understanding of what these various components are, building these types of systems, where do we implement them? How do we decide how and when to use them? So we go back to the same thing. We have a set of guidelines which are suggested, right? Using Promise Theory, owning your own data, keeping your systems small, reasonably small, so they're easy to test. Clustering for resilience, using a toolkit or a framework that provides these features. Understanding that things like consistency and availability and all these types of things are defined by your SLA, not some toolkit or some document that you read. Using polyglot persistence. And then what you end up is this style of diagram. So where you have your different microservices, and on the left there happens to be 4 in this cluster, and they're using some type of NoSQL database, say, perhaps. In the center we have some search mechanism, and that's not using any warm storage. It's hot and memory cache, say, something like that. And you will decide with your business folks and what the SLA says as to what is the best way to lay this out for each system. When deciding between CRUD and event sourcing, if you care about historical auditing, use event sourcing. Auditing, use event sourcing. If you need to shard your data in a significant way, use event sourcing. If you want strong consistency, historical strong consistency, then use CRUD and understand that you are most likely, you can still do event sourcing, obviously, in a relational database, right? And you can still use the relational database semantics with transaction management. It's just when you go to cluster and replicate the data, that's where it's not as easy if you're using traditional event sourcing. But you need to take a look at that and make that decision. And again, if you only care about current state, then I would definitely use CRUD in that situation. So now we have our system. We've layered onto it the decision of where we're going to use CRUD and where we're going to use event sourcing. And so now we have, in this particular one, we've changed the search cache, or the search cache is not historically capturing the data. It's just replacing the data in memory, whatever that data structure is. And the other 2 ones are using event sourcing. Now we want to take a look at fast data and how we're going to implement that in our system. Remember the fact that fast data is based on streaming. Streaming has these synthetic boundaries for time, temporal boundaries. And understanding that in many cases fast data is orthogonal to your microservice architecture and so forth. And then, as I had mentioned earlier, think about it as a backplane. One of the mistakes that I believe is being made today is a lot of folks are starting to take that data backplane and use it as their persistent source of truth. And I don't think that's a good design. Even though they can do that, I don't think it's a good design, because I think you should own your source of truth, nobody else. The data backplane just feeds, right? It's another place that you can grab some data from. So now we take a look at our system, and this is what we end up having. In the center there is our river, our data backplane, and we have all these different microservices around it that feed into it and pull out from it and so forth. And these systems work pretty well. They really do. They're very robust, and they give each microservice insight that they may not have previously had, or that they would have had to request, as opposed to being able to subscribe to or something like that. So we do that, and in this particular example for fast data, we're going to use Kafka. So it's a great dumb queue to use that works very, very well. And the last thing we're going to add to our system is this feedback control. And the different aspects we've already talked through, and I got to be sensitive of time, but we're just about at the end here. And Now, if we take a look at feedback control in ACCA, we have it built in through supervisory control, which gives us our ability to be self-healing, but it's also feedback. The supervisor receives data from the child and makes a decision, and it can do that in a loop. And so now we have our system, and we've implemented tools such as Spark and so forth to provide us the ability to do some of these regression analysis and feedback control type things. So we're almost there. What are we missing? We're going to add insight. And insight is monitoring of the system. And that's the ability to not only monitor the system, but also monitor the monitor. Who watches the watcher? So any monitoring tool you have should also be able to monitor itself and say, hey, I'm having a problem or whatever. So at the end of the day, we have this system that provides all the features we're looking for. In Insight, you can do events and metrics and all kinds of stuff. You can use CollectD, StatsD. There's a lot of tools out there that provide that. We have it for ACCA and so forth. So I want to take the rest and just leave the last couple of minutes for any questions if there are. Okay. If not, thank you for coming out. And I'll be here for a couple of minutes if you have any questions, if you just want to come up. Thank you.